So a warm welcome to all the participants. I think some of you will still come. So just a technical words for the presentation. As I mentioned in the email, during the presentation you can ask questions. Just use the chat, or you can use the raise hand function. You see at the bottom of the screen you have a reaction button. Just click on it, and there is then a button raise hand, and then the Christos will just see that you have your hand raised, and he can answer your questions during the talk. So don't hesitate to ask questions. For the rest, we are recording this meeting, so that, I mean, if some of your colleagues cannot attend, we will share the link after the talk. That's all for me. So now, so first of all, thank you, Christos, for accepting to talk. And now a few introductory words by Marianne, our leader from Austria. Up to you, Marianne. Thank you.
Okay, thank you, Lionel. So dear students, dear leaders, dear Professor Likos, good morning and welcome to our morning talk about the role of entropy in physics, especially in soft matter physics. Let me say a few words about our today's lecturer, Christos Likos. Professor Likos grew up in Athens and studied at the Technical University of Athens electrical engineering. This may be also one of the fun facts, according to Christos, that he is now a professor of physics and he never studied physics. So after his studies at Athens, he moved to Cornell, USA, to work on his PhD thesis. After that, he spent many years as a postdoc in Germany, where he finally got a professorship for theoretical physics at the University of Düsseldorf. Since 2010, he holds a full professorship at the University of Vienna. The University of Vienna is the biggest university in German-speaking countries, and within it, the Faculty of Physics holds a very important role, for instance, regarding the amount of external research associated funding. Christos Likos implemented at the University of Vienna a focus on soft matter physics, which is a quite young and promising research field with increasing importance in physics. He is now, we can say that, one of the worldwide top leading scientists in soft matter physics. And whatever soft matter physics is and what it is about, Christos Likos will tell us. Christos, the stage is yours.
Thank you very much, Marianne, for your kind introduction. At the moment in which you said that I have never studied physics, I looked at the number of participants to see if there are any changes after that. And actually it dropped. It dropped because Lionel left, but I don't take this personally. I think he wanted to leave anyway. So I'm going to mute all participants now for technical purposes. But of course, as Lionel told you, you are very welcome to raise your hand or say in the chat, write in the chat if you have any question. Before I proceed, my most sincere thanks to the organizers for inviting me, but mostly for organizing the International Physics Olympiad. I know from second hand, from talking and seeing how Marianne is engaged, that the leaders are investing an awful lot of their personal time, sacrificing from family, from work, from whatever else they have to do, and they have to be commended for this dedication they have to physics. So as announced, my talk today is going to be about entropy, the role it plays in physics and in particular in soft condensed matter physics. And also I would like to take this opportunity to maybe clarify some misunderstandings that exist regarding the connection between entropy and disorder, because there are many, let's say, stereotypical statements that are stated in most physics books about entropy. Moreover, not even at the university level, let alone at the school level, entropy obtains in education the attention that it deserves for various reasons. But let's take one thing after the other. I wish I could flip my slides. Yes, I can. So a very brief summary of my talk is that I will first discuss the entropy at the level of thermodynamics and or statistical mechanics to get an idea of what exactly it means. And then I'm going to go into the second part to one of the most interesting phenomena in statistical physics, namely phase transitions, the transformation macroscopically of one phase into the other, let's say the freezing of water, for example, upon the change of a tiny change of some external parameter, such as temperature and pressure. And the way that phase transitions are usually framed in statistical physics is a kind of competition between energy that favors order and entropy that favors disorder. I mean, this is the standard, the orthodox interpretation. And then as you change that temperature, beyond some certain temperature, entropy and disorder take over and the system becomes disordered. I mean, that is the standard scenario. But I'm going to argue at this part of my talk that this scenario is misleading. And in fact, entropy can drive very interesting phase transitions. And in fact, entropy can favor order in a large variety of cases, which may sound paradoxical, but we'll see how it comes about. So let's start a little bit with a discussion of entropy. First of all, on thermodynamic grounds. And when I say thermodynamics, I mean ignoring or pretending we don't know anything about the microscopic constituents of matter. You know, one of the big debates, and actually ugly debates, in physics towards the end of the 19th century and up to the beginning of the 20th was the atomic hypothesis. Does matter consist of atoms and molecules or not? And in the absence of experimental evidence for that, many people were shy of defending the atomic hypothesis in public, Boltzmann being then the rare exception, and he had to pay a price for that. So thermodynamics was formulated originally in an abstract, axiomatic, empirical level, as it were, without resorting to any information on the existence of atoms or molecules. And it was in fact Rudolf Clausius, an eminent physicist in the second half of the 19th century, who introduced the notion of entropy. He said, in an abstract way, entropy is a function of three variables in the system: of the internal energy U, which is here, the number of particles N, and the volume of the system V. And then the temperature, the absolute temperature of the system, is defined in this particular language as the partial derivative of the entropy with respect to the energy, 1 over T is that, and it's positive. And one of the postulates of thermodynamics is that the entropy is a monotonically increasing function of the energy. And what Clausius recognized, what has been recognized even before Clausius, first of all, is that heat transfer, so heat is a form of energy. That is something that people had finally appreciated by the 19th century. And Clausius established the following thing. He said, well, heat goes only from the hotter object to the colder object in spontaneous processes. You can never transfer heat from the colder to the hotter object spontaneously. You have to do work to do that. But if you talk about spontaneous processes, and you take a hot object and you bring it in contact with a cold object, you just keep this contact very shortly, so that a very small amount of heat is transferred. Okay, so there is a heat delta Q going from the hot to the cold. What Clausius said about entropy is the following. He said entropy is the amount of heat, this tiny amount of heat, divided by the temperature of the body. Now, which body? The hot body has a higher temperature, right? So the change of entropy of the hot body is this delta Q divided by the higher temperature, and it is negative because heat goes away. So the hot body experiences a reduction of its entropy. Delta S hot is delta Q divided by T hot. At the same time, the colder object receives that heat, so it experiences an increase of its entropy. But delta S cold is the same delta Q, but now divided by T cold, which is lower than T hot. And this delta S hot is positive, right? Because the cold body receives heat. But now you see the delta Q is the same in the numerator of both, but T hot is higher than T cold, which means the increase of entropy of the cold body, of the body that receives the heat, is higher in magnitude than the loss of entropy of the hot body that kicks the heat away. So in total, the combined hot and cold body together, after coming in contact, they have increased their entropy. The total entropy of both has increased under the condition that the total energy of both is fixed, because the energy that was lost by the first was gained by the second. And that is the core of Clausius' statement. I'm just put a few sentences here that say it's a second law of thermodynamics that says, well, in a spontaneous process in a system in which the total energy is constant, the entropy can only increase. There is no spontaneous process that decreases the entropy. And this is precisely the aspect of reality that gives us a notion of the time arrow. This is precisely the property of nature that defines the flow of time and that allows us to distinguish the past from the future, that allows us to distinguish when a process is running forward in time and therefore it is possible, or it is running backward in time and therefore we call it impossible. If you take a film and you play it forward or backward, you can certainly tell for most cases which is which. The reason why you can tell that is because spontaneous processes always lead to an increase of entropy. There has been a lot of discussion about the second law of thermodynamics and about how is it possible to bring together the fact that microscopic laws are time reversible, but macroscopic laws are not time reversible. Boltzmann's work on probability gave us a very good idea about why this is happening. I will say a bit about it later. And so you see the second law of thermodynamics, despite it being debated, is really an anchor of our experience in physics, of our experience with nature, this arrow of time. There has been a very famous scientist, we'll see who it is in a moment, that made this very strong statement. And he said, the law that entropy increases holds, I think, the supreme position among the laws of nature. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. You can put in question Maxwell's equations. If it is found to be contradicted by observation, well, experimentalists do bungle things sometimes. The person who said that was a theorist, I think. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. These are strong words. And the paradoxical thing about this second law of thermodynamics is that it is probabilistic in nature. The law of physics in which we have the most trust, because we can see if the arrow of time is violated, turns out to be probabilistic. We'll come back to it in a moment. So, to prevent any kind of misunderstanding, I am not going to put in question the validity of the second law. It is valid. I wanted to point out in this talk how our conclusions that come from the second law can be misled and or misleading. Okay, so the person who said that was Sir Arthur Eddington at the beginning of the century, certainly one of the leaders of physics in all times. So this is, I'm not going to discuss every slide I have, but here is a schematic that I copied from Cullen's famous book in thermodynamics, and shows the two equivalent formulations of the second law. On the left part, so you see I plot entropy on the vertical scale, entropy in this left-right axis, and on the diagonal, this 45-degree axis, there is a collective variable with all the constraints of the system. For instance, the fact that you have the hot and the cold separated, you lift the constraint, you let them come in touch, and what happens is that at constant energy, you see entropy is going to find a maximum. So the equilibrium state of the system is this A. You can formulate equivalently and say, well, if I have now the entropy fixed, so if I cut this surface, the entropy energy constraint surface, if I cut it with a horizontal plane at fixed entropy, the energy must be a minimum of the combined system. It's an equivalent statement because that surface is convex. Okay, so I see no questions up to this point. I check the chat. nobody has a question, but please interrupt me if you feel you get lost at some point. Good. Now, this is all good and valid, but remember, in experimental situation, we can hardly control the entropy of the system. Let me flip back to this slide. This is the formalism that I'm interested in. It says, then the energy is minimized with respect to any internal constraint if I keep the entropy fixed, but it's impossible to keep the entropy fixed in most experiments. So we need a formalism in which, for example, the temperature is kept fixed, which is the conjugate variable of the energy with respect to the entropy. And as we all know, the way to go from a formalism that contains entropy, particle number, and volume to a formalism that contains temperature, particle number, and volume is to perform a Legendre transformation, introducing the Helmholtz free energy of the system, F. I'm going to work with F for the rest of the talk. So the energy of the system minus the product of temperature times entropy of the system. This quantity is minimized with respect to any possible internal constraint. So if I lift all possible constraints that I have regarding the distribution of energy, the distribution of particle number, or the distribution of volume between two systems, then the free energy is going to be minimized. This is the principle of equilibrium in thermodynamics for a system that has fixed temperature, fixed particle number, and fixed volume. Okay. So, for instance, if I have a container, it is kept at constant temperature, and the total volume is also fixed, and the total particle number is fixed. And I imagine that I make a separation of this total volume, and I put different particle numbers per unit volume on the two subvolumes. This thing has a higher free energy than the free energy that I will have if I remove this compartment. Because if I remove the compartment, the density will homogenize among the whole volume. Any constraint I put in the partition of the particles between the two subvolumes is going to bring about a higher free energy than the equilibrium. That is the statement that follows. And certainly you can see that in this way we obtain irreversible processes, because you can imagine having a container and I put the same gas on both sides, but on the left side with the wall separating, on the left side the gas has a higher density than on the right side. Now I pull the wall off and the density homogenizes. The reverse procedure is not going to happen. When putting back the compartment is not going to make the gas on the left being denser. So this is a process in which the entropy has grown or the free energy has become lower. Okay, so that is the quantity I would like to work with. And this, up to this point, this is all thermodynamics, right? No discussion has been made about the atomistic nature of matter and so on and so forth. The connection between microscopics and macroscopics is the task of statistical mechanics, and it is the intellectual debt that we have to Boltzmann, essentially, but also to Gibbs, who made the connection between the so-called microstates of the system and macrostates of the system. So this needs maybe a little bit of explanation. So I'm going to try to explain it with a more maybe familiar example. Suppose that you have a die and you roll it 10 times. Okay, and every time that you roll this die, you write down what was the result of this random experiment. So the sequence of the 10 numbers that you obtain after throwing the die, after rolling it 10 times, this is called a microstate of the particular experiment that you have performed. So the first rolling gives you a 2, the second rolling gives you a 4, the third gives you a 5. So 2, 4, 5, until the 10th roll. This is a microstate. And given the fact that every rolling of the die can have 6 possible outcomes, and if you roll it 10 times, you obtain 6 to the 10th possible microstates of the system. Okay, it's a rather simple case. 6 to the 10th is not a small number, but it's still very, very small compared with the numbers we have in many body systems. So you have this large number of possible microstates, and now you do the following. You go and say, well, I would like to group those microstates in subclasses according to some criteria. For example, what you're interested in is the sum of the numbers, okay, the sum of the numbers that you got in any microstate, which can vary in the particular example I gave you between 6 between 10, this is the case in which all of the rollings gave you a 1, and 60 in case that all of the rollings gave you a 6. So you say, I want to group the microstates according to the sum of the outcomes that came. This grouping constitutes classes of macrostates because the sum of the numbers is a macroscopic variable, is a macroscopic observable whose determination includes a very large number of possible microstates. Okay, so this is the definition that we have between macroscopic states and microscopic states, macrostate and microstate. Okay, so if we now transfer the example of the rolling die to a much larger scale, and we take the number of molecules of a gas, of air in a room, what is a microstate of the system? Well, a microstate of the system is a very big object that tells you what are the positions and the momenta of every molecule in the room in any particular point of time. You can easily imagine, or you can maybe think a little bit and contemplate how incredibly huge the number of microstates of the system is. And now you say, okay, this is a very big number. Let me introduce a criterion that takes this large number of microstates and groups them into larger macrostates. What is a possible criterion? Well, a possible criterion could be, for instance, the density of the system in the left half of the room as compared to the density in the right half of the room. Let's take the difference between these two densities as a criterion for creating groups of macrostates. And what it turns out, by calculating the probabilities, is that the number of microstates in which this difference is 0, that is, in which the density on the left and the density of the right are roughly equal, is immensely, unimaginably, unfathomably higher than the number of microstates of any other state in which there is an imbalance of density between the right and the left. Okay, it is incredibly more probable to have equal distribution of densities on the right and the left of the room than it is to have a higher density on one side of the room than you have on the other. The probability, that is, that air leaves one part of the room and it all concentrates on the other, be careful, is not 0. It could happen, but it's so ridiculously improbable that it has never been observed and probably will never be. Moreover, if such a fluctuation of the air leaving one part of the room and all going to the other ever happens, in very, very short time, it is going to be pushed back into the other half and equilibrium will be restored. So the law that a system, like a macroscopic system, like the air in this room, remains homogeneous throughout the room, the law that says it is impossible that all of the air goes into the one side of the room is not as strict of a law as the law that says you cannot exceed the speed of light. The law about the distribution of air in this room is probabilistic in nature. It is not deterministic in nature. I already see a question in the chat, so it's a good point to interrupt and look. Let me click on the chat. That is Clemens Emery. Even if the Kirchhoff's law is a kind of a sub-microstates of the propagation of electromagnetic waves, Clevis, shall I, if I can find you, can you unmute yourself?
Yes, I'm here.
You're here. So thank you for the intervention. Could you please tell us a bit more about this comment?
Yeah, what I wanted to say is when you talked about microstate and macrostate, and I was thinking, and there was a debate how the current moves through the wire, and the Kirchhoff's law was kind of, we always use the Kirchhoff's law, but when you dive deeper, Kirchhoff's law is like, it tells how the charges in the wire will act, but they all act with electromagnetic waves, and it's like the sum of all the acting of electromagnetic waves in the wire that kind of results in the Kirchhoff's law. So is Kirchhoff's law a manifestation of the microscopic nature of the current? Yes, and also the electromagnetic waves. Yeah. Okay. Okay. Well, thank you for this. It's an interesting
remark which I hadn't thought about, but yeah, sounds valid. Thank you.
Thank you too.
Okay, so going back to what I was saying. So if someone showed you, let's say, a simulation or some kind of set up pseudo experiment in which you saw that a signal travels faster than light, I mean, it cannot happen, we know it, you would not have any spontaneous reaction immediately saying, oh, that is impossible, unless you saw some other consequence of this violation of causality or whatever. But something that is a very strict law of nature, like C cannot be exceeded, does not strike your eye as impossible at first sight. On the other hand, if someone played for you a movie that showed all the molecules of the room painted in some color, leave the right part and go into the left part, you would say, oh, but that's impossible. This is a manipulated simulation. This cannot happen. Although this second scenario is not prohibited by the laws of nature. The second scenario is probabilistically impossible. The first is deterministically impossible. And still, the arrow of time is so much entrenched in our experience that we immediately recognize procedures that violate the second law. Okay, and this is, I mean, how the second, this is how Boltzmann essentially then, first of all, calculated the probability of any microstate. He said, well, if all the microstates have the same energy, then they are equally probable. So if W is the total number of microstates that exist in the system, the probability of each one of those is 1 over that number W. And of course, the other thing that he did not say, Max Planck said, but it comes out of Boltzmann's writings, is that the entropy, now Boltzmann can define the entropy in a microscopic way. He says, well, take this number W of possible microstates that are associated with a system at a given energy, take the logarithm of it, and that is the entropy. The constant K that is in front, Boltzmann constant, is just a conversion constant between degrees Kelvin and joules. It has no particular physical meaning. The main thing is that the entropy is the logarithm of this possible number of microstates. Okay. And now you see, this number of microstates that you have is hugely, vastly exceeding the number of other microstates for systems for states that are not in equilibrium. And this is why we see macroscopically this uniform distribution of gases in rooms, this uniform density of liquids where they are in a container, and so on and so forth. Every process that occurs spontaneously does so because the end state has a much higher probability than the original state. The number W of microstates of the final state is much larger than the number W of the two original states combined. By the way, this is Boltzmann's grave here in Vienna at the Central Cemetery on the way from the city to the airport. But I must confess I have not been there yet. Okay, the other giant who contributed, who co-founded statistical mechanics with Boltzmann was Gibbs, American physicist, Josiah Willard Gibbs. You know him also from the famous Gibbs paradox. And he completed Boltzmann's formula by considering now also microstates that don't all have the same probability. So if you have in a fixed temperature and not in a fixed energy, different microstates have different probabilities, and he redefined the entropy as the sum of the probability times the logarithm of the probability of every microstate, with a minus in front, clearly because the PNs are less than unity, and otherwise the entropy would be negative, but the entropy is positive. Okay, so this is the broad introduction to entropy from statistical mechanics that I would like to present. We're going now to move forward to some more specific examples. Before I do that, is there any question that has arisen from any participant? I make a short pause to see if a hand is raised or if the chat gets read. I don't see any such reaction, so let's move ahead. So This is now, well, you saw that, there is someone in the chat. Let me click. So Clevy says, why should there be a log or an NL? Is there a simple explanation of why should there be a log? Okay, yes, thank you, Clevis, for this. There is the entropy, let me go back. There is a property of thermodynamic functions, namely that they are extensive. So they scale linearly with the number of particles that you have in the system and with the volume. Now, it turns out, and this you can do this calculation easily, the number of microstates W that you obtain here has a dependence on the particle number that has this particle number as an exponent. So it's a number raised to the power n, n being the particle number. If you want to create out of this W a quantity that is extensive in n, you have to take the logarithm. So the logarithm of something to the n is n times the logarithm of that something. Have I answered your question? Yes, okay, great. So let me now go to another very famous name in statistical physics, but not as much known as a person. This is Ernst Ising. Ising was, or Ising for our American friends. Ising was a PhD student in Germany at the beginning of the 20th century. He was working with Lenz, the same Lenz that has this Lenz law in electrodynamics. And his advisor told him, well, why don't you look at this very simple problem, simply stated problem, take a lattice, take a collection of points regularly distributed, let's say a square lattice in 2 dimensions. And on every side of that lattice, put a spin, SI, and this spin can only take 2 values, +1 or -1. I mean, Lenz was informed about quantum mechanical spin, but this is a classical model. There is no quantum mechanics involved. And so let the energy of the system have a very simple expression. Take the product of 2 neighboring spins, add over all possible neighbors, and multiply by a constant j, which we're going to take as positive in this case. So that is the so-called Hamiltonian function of the system, the total energy of the system solution. Okay. Ising worked on this system. He didn't go very far in his PhD. I think he could solve the 1-dimensional model explicitly, but that's kind of a boring model. Then Ising had some Jewish roots, so he had to leave Germany. He went to the States. He became a physics teacher, and you can see him here teaching his pupils with a famous experiment on angular momentum. He became almost 100 years old and passed away maybe 10 years ago. His model is much more famous than he ever got because it is a prototype of phase transition. So I'm going to focus a little bit on this. So let's look at this Hamiltonian function. This is the total energy of the system. Remember, J is positive. You can even set equal to 1 if you wish, and there is a minus sign in front. What does this mean? It means that if you want to minimize the energy of the system, the best you can do is make all your spins pointing the same way. So if a spin is pointing up, its neighbor is also up, and its neighbor is also up, and all neighbors are up. This way, every term in the sum is equal to 1, and with a minus, you have an energy which is minus n times the number of neighbors divided by 2. You can achieve the same result if you make all spins pointing down, right? So the ground states of the system are 2. Either all spins going up or all spins going down. And this is, as you can imagine, or some of you may have guessed, this is a model for magnetism. So if you only want to minimize the energy, you have 2 ground states, spins up or all spins down. However, so the magnetism, excuse me, let me go one step back. As we say in that case, all spins pointing up, the magnetization equals to n times, is equal to n. All spins pointing down, the magnetization is equal to minus n, n being the number of particles. However, if you think now statistical mechanically, if you take any state, macroscopic state, in which the magnetization is not just n or minus n, you realize that the possible combinations you can make to reach that state are huge. There is a very large number of possibilities, for instance, to flip just one spin. Just by flipping one spin, you have n choices to flip just one spin. If you flip 2 spins, not just one, the choices become even more and more and more. So the more disordered the system is, okay, that is, the more your magnetization tends towards zero, tends toward being balanced, equal number of spins up, equal number of spins down, the higher the number of microstates you have. It's a little bit like the air in this room. The more homogeneously it is distributed in the room, the more microstates you have. Accordingly, what entropy favors, because entropy wants to grow, right? What an entropy is logarithm of omega, and omega is huge if you have zero magnetization, but omega is very small if you have large magnetization. So entropy favors disorder. And this is well represented mathematically, if you like. I skip all the details. Here you have the free energy of the system. Please ignore the subscript var. It comes from some mean field approximation called variational approximation. We don't care about it. So you see the free energy, as I said before, is energy minus temperature times the entropy. And we want to minimize this F. Now, the black curve is the energy. See, it is minimum when the magnetization is -1 or +1. I now take the magnetization per particle. So the black curve wants to drive the system towards very, very low or very high magnetization. The second term, minus S, before multiplying with the temperature, minus S, or minus the entropy. So minus the entropy wants to be as small as possible because the entropy wants to be as large as possible. This one has its minimum at magnetization 0. So the two terms are antagonistic to each other. You add them together after you have multiplied the red curve with the temperature. So what is the result of this? Look here, if the temperature is low in the blue curve, it is 1/3 of the so-called critical temperature, then the energy dominates and the system is magnetized, right? The sum of the two has its minimum at -1 or +1. Now, as I start increasing the temperature from blue to green, the minimum moves towards 0. At the so-called critical temperature, the minimum is at 0, and at higher than critical temperature, it remains at 0. So at low temperatures, energy dominates, and we have a magnetized system that has a non-zero magnetization. At high temperatures, entropy is dominating and drives the system toward zero magnetization, which is disorder. That is the prototype of phase transitions in most areas of condensed matter physics. I call it hard condensed matter physics, as opposed to soft condensed matter, about which I will talk in a moment. Okay, so this is the general mechanism that most phase transitions have. I don't know if you have seen it before, and since this is a bit of a technical slide, I make another short pause to see if there are any questions on this. There is a competition energy entropy. I wait a couple of seconds to see if questions arise. Doesn't seem to be the case. Okay. So it is on the. So this is an example from a model that is written on a lattice in which your things cannot move, spins cannot translate. If we go now to a more realistic system like a fluid, argon. Okay, and then argon atoms have such a typical interaction potential between each other. There is an attraction between the atoms, although they are not charged or anything like that. This comes out of dipole fluctuations. It's a dispersion force. I'll say more about it in a moment. And then if the two atoms approach very close together, there is a huge penalty that they pay in potential energy. You cannot put two atoms very close to each other. The reason for that is not Coulomb, is not repulsion between charges. The reason for that is a Pauli exclusion principle. Right? If you bring two fermions, like two electrons, very close to each other, there is a huge quantum mechanical repulsion between the two. So this is a typical interaction potential between two atoms in a liquid. And if you do the statistical mechanics, if you do the phase diagram, you see that it brings about this attraction that you have here brings about the famous gas-liquid coexistence. So on the horizontal axis, you have the density of the system. On the vertical axis, you have the temperature of the system, right? Analogously to the coexistence between negative magnetization and positive magnetization. Here, if the temperature is low enough, you have the coexistence between gas and liquid. You have the phenomenon that a fluid is separated by its vapor by an interface, a phenomenon we see every day when we drink a glass of water, right? The water makes an interface with the air coexisting with its vapor. So at low enough temperature, energy, condensation energy, the fact that the particles like to stick to each other because of this attraction wins, and you have the formation of a liquid. At high temperature, entropy wins because the temperature is high enough, the molecules unstick and they make a uniform fluid, no separation between gas and liquid, a uniform fluid that fills space. I leave the solid out of this discussion because the energy entropy competition pertains precisely to this part of the phase-time. So we see this is a continuous analogon of the Ising model. What the Ising model does for magnetization, this model does for liquid-gas coexistence. Okay, and so this is again energy versus entropy competition, and this has given rise to the usual, let's say, interpretation of the role of these two quantities in statistical mechanics. I show you a few examples. This is a cartoon from this famous book by George Gamow from the 50s, and he made the cartoons of his book himself, and he said, well, at absolute zero, energy dominates and everything's nicely ordered. At room temperature, well, it's not still hot enough for this thing to become total chaos, so the thing is more like a liquid. The pupils remain on their chairs, but they start, making some fuss and kicking each other and jumping around. And then if you increase the temperature even more, all hell breaks loose and all bonds break and chaos results. And this kind of interpretation permeates through the whole culture of physics and maybe popular culture. I have fished a few sketches from the internet that always show this scenario. Increasing entropy goes from highly ordered to more disordered. Again, this is another sketch. There is probably a temperature running or entropy running in the horizontal axis, order, low entropy, chaos at high entropy. Entropy causes order becoming disorder, increasing entropy, solid to liquid, the same kind of mentality all over, everywhere you look, in physics books, in cartoons, in popular culture. This is one that I like. This is the picture of the Department of Energy of the United States of America. You see how nicely ordered it is, right? The windows and everything. This is a cartoon of the Department of Entropy, and it looks a little bit like the office of the typical university professor in physics, as it were. So this is the state of affairs, right? Energy is brav, as the Germans say. Is a good girl, and entropy is making fuss all over the place. It's interesting to point out in this historically at this point that when Clausius introduced the term entropy in the 19th century, he purposefully wanted to have a word that sounds a bit like energy. So he looked back into he had learned some ancient Greek, and he constructed this pseudo-ancient Greek sounding word called entropy, which means something like a force of change, something like that. I mean, Cooper, the guy who invented Cooper pair, said that in introducing the word entropy, Clausius managed to have a term into physics in which everybody agreed what it means, and that is nothing. I mean, nobody understands what entropy really means, even linguistically. Anyway, maybe it is the fact that entropy is associated with chaos is part of the reason why in our educational system we talk so little about entropy. Maybe it's considered confusing or too complicated or too annoying. I don't know. But certainly, I don't think if you ask a graduate of the school to tell you what entropy is, that you will get a satisfactory answer. What interests me for the rest of the talk is, well, is entropy always that bad? I mean, is entropy an agent that always destroys things and is going to drive us into chaos sooner or later? And how can we test this idea? So again, let's go back. Remember, the free energy F is U minus ds. So here's a silly question. Are there any statistical mechanical systems in which the energy is U in the F equal U minus ds? This U is identically zero? Well, a trivial example are non-interacting systems, ideal gases. They have U equals 0 apart from the trivial kinetic energy. But then ideal gases are really boring. They don't have any phase transitions. And so they are not appropriate systems to test the question if entropy is always bad. We have to think a bit or to work a bit harder. And this is where soft matter comes into place. So let me skip this slide. Let me just give you a very short introduction to what soft matter is. So you all know hard condensed matter, so metals and insulators and things that are very hard to deform. The building blocks of these materials are atoms and molecules, but there is another class of materials whose building blocks are macromolecular aggregates such as colloids or polymers. And these materials, while they are present in everyday life, because every time you shave, if you are a man, or you use any gel for your hair or anything like that, or toothpaste, whether you are a man or a woman, when you use a toothpaste, you see it's a material that's very soft, very easily deformable with your own fingers. I mean, also living matter is very soft. Our skin and tissue is very soft. So these soft materials the constituents of those are macromolecular aggregates, bigger aggregates dissolved in a molecular solvent. Blood, for example, is a typical soft matter system because it has big entities, red and white blood cells, dissolved in a molecular solvent, which is the plasma, which is mostly water. Blood also contains many other things, of course, like protein, salt, and so on. It's a very complex liquid. So viruses, DNA, proteins, chemically synthesized colloids and chains and polymer chains, branch polymers, they're all soft matter. And why is soft matter soft? Well, you can make an easy scaling argument that tells you that the shear modulus of a material is the ratio of an energy to a size, to the power cube. And of course, the size of colloidal particles are 1,000 times bigger than the size of molecules. So easily the shear modulus of soft matter is 6 to 9 orders of magnitude larger than the shear or compressibility modulus of hard matter. And this is why you can deform soft matter with your fingers, but if you want to deform hard matter, you need the powers of an earthquake. Okay, so that's hard matter. That's soft matter: polymers, colloids, surfactants, liquid crystals, membranes, and biological systems. The reason why now soft matter is interesting is the following. If I go back, forget all the algebra, let me go back a little bit to this interaction I showed you before, right? This red curve with this ubiquitous attraction between the dipoles. Where does it come from? If I have two atoms, they are neutral electrically, but they have a spherically symmetric charge distribution, but there are spontaneous fluctuations. So there are spontaneously, the distribution because of quantum mechanical fluctuations deviates from sphericity. Averaged over time is spherical, but at every point in time, it has a deviation from it. So there is spontaneous dipoles that emerge. And if I bring another atom in the neighborhood, this dipole here, which spontaneously formed, induces a dipole on the other. And it does it in such a way, you can show it, that these dipoles most of the time attract each other. This is the source of this attraction. And you cannot, if you're doing atomic physics, there is no way to influence it. It is going to happen because it is based on quantum mechanical fluctuations. You cannot suppress it. However, if you are not doing hard matter, but doing soft matter, it turns out that this is now the dipole-dipole attraction. There is a coefficient in front of that dipole-dipole attraction, forget all the algebra, which the strength of this coefficient depends on the difference of the dielectric constants of the molecule minus the dielectric constant of the solvent. So if you match the dielectric constants of your colloid and of your solvent, you can kill this annoying attraction, and you can go back, sorry for my flipping, you can have, instead of this red curve, which has this attraction, you can have essentially a curve that is 0 and then goes to infinity. So you can have what we call a steric repulsion. You can mimic in soft matter physics the energy of interaction between two billiard balls. means no interaction if they don't overlap, and infinite interaction if they try to overlap. Which means every allowable configuration of the system has zero internal energy because overlaps are not allowed, and every non-overlapping configuration has zero energy. And that's a crucial point to keep in mind. In soft matter, we can experimentally materialize what were called a hard sphere interaction. So we can materialize systems which little colloids don't overlap, they are not allowed to overlap, but as long as they don't overlap, have also zero energy with each other. Is this point clear, or do we have a question here? I don't see anything in the chat and I don't see any hand raised. So let's now take this along. Right, so this is what I'm writing here in words. So the interaction potential between any two particles of size sigma, sigma is now the diameter of my colloids, is infinite if the interparticle separation is less than sigma, so no overlaps allowed, and zero if R is larger than sigma. Okay, so the interaction energy in any allowed state of the system vanishes, it is zero. All microstates have the same probability because they have the same energy. And moreover, the free energy of the system, since U is zero, is just minus Ts. And this is now an example. This is a situation that occurs only in soft matter systems. They are at the same time thermal and they have no internal energy. The whole free energy of the system is entropy. Entropy dictates the thermodynamics of the system. Entropy determines everything. Accordingly, the state of equilibrium of the system, the state that you will see when the system has reached its equilibrium thermodynamically at any condition of density or pressure, is the state that maximizes the entropy, right? Minimizing F means maximizing S. Okay, so let's keep that in mind. Under any conditions of fixed temperature and fixed density, the system always maximizes its entropy. So the free energy is all entropy, and the question is, can these systems have non-trivial behavior? Because you see, according to the traditional interpretation of entropy, what these systems can do is just always be chaotic, always be as disordered as possible, right? Entropy loves disorder. So if that interpretation is true, it would mean that entropic systems are always disordered. Can we test this? Is this true? Okay, now here is, I apologize for the poor quality of this slide, which is due to my scanning, but this is a figure from a legendary paper. There were two of them occurring, as you see, in subsequent pages of the same volume of the Journal of Chemical Physics. So Wood and Jacobson did a particular kind of simulation called molecular dynamics. Alder and Wainwright did another kind called Monte Carlo. And they did a very simple thing in a computer. They took a system of hard spheres and they simulated it. Okay, they just let and that they solved Newton's equations, or they did some Monte Carlo, it doesn't matter. And they observed after a very long time what was the physical state of the system. So on the horizontal axis here, you have the so-called specific volume, which means if this is large, if the specific volume is large, it means that the density is low. And if the specific volume is low, it means that the density is large. And they calculated the pressure of the system in that configuration. So they took 32 particles in the box, they calculated the pressure. They made the box smaller to increase the density, they calculated the pressure again, and so on and so forth. And what you see here is that as you increase the density, the pressure grows, it remains metastable for a while, but then it jumps. It makes a jump suddenly to a higher pressure. There's a second branch of pressures that occurs here. Actually, what they observe is a phase transition from this branch to this branch, because the pressure can only be a single valued function. It means that at some intermediate state, the pressure goes from one branch to the other. So there are two coexisting phases here. At low density, there is one phase. At high density, there is another phase. So the system undergoes a phase transition. I mean, that's a surprise. Something that only has entropy has a phase transition from something to something else. So what are these somethings? Clearly, at high densities, at low density, so at high volume, specific volumes, the system is a liquid, right? It's a fluid. The particles are in the box, so they are just hard spheres, and they are moving around. So what is the phase at high densities? What does the system do at high densities? And it turns out, and this is something that people figured out in those papers and further analyzed in the future, that what happens as you increase the density is that the system crystallizes. So here is pressure versus packing fraction. You see, you increase the packing fraction, so the density of the system, and at this particular packing fraction, it makes a phase transformation from a liquid to a solid, to a so-called phase-centered cubic solid. And this is another simulation, and this is another theory. This scenario has been confirmed since then in thousands of works. So that is a very unexpected thing, because you have a system whose free energy is all entropy. And still, if the density is high, the system crystallizes, but the crystal is clearly an ordered state, right? So at this high density, look at the free energy of the liquid. It is this broken curve. And look at the free energy of the solid. It is the continuous curve. So what do we see at high densities? The solid has the lower free energy than the liquid. And let's go back. The solid has a lower free energy than the liquid, meaning the solid has a higher entropy than the liquid. I mean, that was a shock for people when these papers were published in '57, that you can have a situation in which a solid, which is an ordered phase, okay, has a higher entropy than a liquid, which is a disordered phase. And this is the reason why people didn't believe these results for many years. It took at least 1 decade for people to start taking seriously the prediction of order and Wainwright, and really contemplating how is it possible that a state that has order also has a higher entropy than a state that is disordered. Now, before going into the explanation of this puzzle, let me give you another example which pre-existed, in fact. This example is due to Onzaga, one of the giants of statistical physics, who did not work with hard spheres. He was also a theorist, but he worked with rods, if you like, with molecules, well, theoretical molecules that look like this, right? They're just elongated, they are cylinders, and they have the property that they cannot overlap. Okay, overlap is not allowed in any configuration, but otherwise they have no energy of interaction. So this configuration is equally probable as this, as that, as any other one, and they have energy 0. So what is the physical state of such a system, such a collection of cylinders, of long cylinders? And you start increasing the density. What is going to happen? And Onzaga had already predicted theoretically in a kind of abstract model that as you increase the density, the system is going to order. In particular, the order that he predicted was the transition between a so-called isotropic state in which all these molecules translate and rotate freely, to a state which is called nematic, namely in which the molecules still translate, but they don't rotate. They are all oriented in a particular direction of space. Okay, and you would say certainly the second state in which the molecules are all oriented has more order than the state in which molecules can turn around in all possible directions. And still the system only has entropy. So why would it go on entropic grounds from a disordered to an ordered state? Isn't that a paradox? So if you think about it, it's not paradox at all. The problem lies in the concept that we have about order. This optical idea of what order is not the same as what statistical mechanics thinks about order, because what actually entropy means is what is the number of states that are available to the system. And now let's take a look. If I take two molecules like this and I say, well, choose your orientations freely, do whatever you like. You see, if they happen to have this orientation perpendicular to each other, then the center of the second molecule cannot approach the center of the other molecule by a distance which is as big. So there is a huge space around the first molecule that remains unreachable to the second if it chooses to have this orientation. On the other hand, if it chooses to have this orientation, it can now come much closer. So there are two kinds of freedom that the molecule has to negotiate. Do I want to sacrifice some orientational freedom to gain translational freedom, or do I prefer to have both freedoms, but in this case, I sacrifice translational to have orientation? And so it is now a competition between two different kinds of entropy, the translational entropy versus the rotational entropy, and that's what determines the game. Optically, what you see is a state that results, which has more order, but this word order is an interpretation thing. You call it order because you see the molecules like being all pointing in the same direction. So one particular thing, orientational order, is now stronger than in this case. But translationally, the system is more disordered in the sense that now each molecule has more free volume to move and to explore than it would have if I had allowed orientational disorder everywhere. It sacrifices some order in one case to obtain disorder from a different point of view. And so for the Onsager model, this is a bit more transparent. For the hard sphere model, I'm going to skip all this mathematics. The question amounts to the following. If I consider any typical disordered configuration, like a liquid in the system of hard spheres, what are the typical voids that I have in which I could introduce an additional molecule? You see, if it is disordered, the voids that I have around each particle are very irregular. This system is not using space in a particularly efficient or smart way. But if I make an ordered case and I remove a particle to see what kind of void was there, you see how much bigger the void is in which I could introduce this particle. The fact that the fact that the particles arrange themselves in a regular way allows them to use space more efficiently, meaning the space that each particle has to move is now optimally used as opposed to a disordered configuration. And you can see this. You can see this in penguin colonies, in fact. You know, penguins, they get very crowded in the Antarctica, but each of those animals wants to get as much sun as they can, and they want to have optimal space from the other animals. So if you look carefully at those pictures, you will see that they have big regions in which they form lattices, they form crystals, just in order to maximize the available volume they have around. So an ordered configuration, optically ordered, offers the most freedom of free space around each given particle. It maximizes entropy by making optimal use of space. Okay, there is no violation of second law. Entropy is still larger, but the state is more ordered optically than the liquid one. Okay, so let me. I mean, I have a few examples. Well, just to convince you that this is not just theory, this hard sphere freezing was confirmed experimentally in 1986. This is a collection of PMMA spheres, colloids in a particular solvent, which suppresses the attractions. And now the density grows from left to right. And you see on the left, we have a packing fraction less than about 0.5, and they do scattering of light. And in this intermediate density where fluid coexists with crystal, and crystal is here, you see the Bragg reflections. You see these very bright crystal-like reflections, meaning that really a hard sphere crystal has formed. Let me give you one final example regarding condensation, in which entropy again can bring order. This is a mixture. This could be a mixture of colloids. These are the big blue particles, and polymers. These are the smaller green particles. But let's consider it now as a theoretical model. So here's the idea. The small particles cannot penetrate into the big one. So there is a hard sphere interaction between blue and green, which means that the region which is colored yellow, including the interior, is not accessible to the centers of the green particles. Okay, it's not accessible. They cannot go in there. So if my two blue particles are a big distance apart, the total volume available to the green particles is the volume of the system minus the sum of the volumes of the two yellow plus blue regions, right? So these two regions, blue plus yellow here, blue plus yellow there, are excluded, depleted. No green particle can go there. So if the two big particles are far apart, the available volume is the whole volume minus these two. Now, bring on the other side, now the two blue particles closer together so that their yellow depletion regions overlap. You realize that now the available volume for the green particles has increased because there is an overlap between the blue regions that is counted twice. So you have to take it once away. So look at this. You have in the second situation in which your big particles are close, there is more entropy available for the green particles than it is in the first case because the entropy scales with the volume available. Accordingly, for entropic and only for entropic reasons, there is an attraction, there is an attraction between the two big particles. If the entropy is higher in the second case, it means that the free energy is lower, so the two big particles like to stick together because in this way they free up volume for the small particles. You can think of it alternatively by saying in this second configuration, the small particles hit them from the sides, so they push them together. Accordingly, if you make a solution of many of those big particles and many of those small particles, there is going to be some attraction and therefore condensation, formation of a liquid of order of the big particles only on entropic reasons. Entropy can even cause you attractions. Entropy can make a liquid-gas coexistence. So now you go into the case in which you have a separation between liquid and gas entirely because of entropy. You can reproduce almost all of the phase transitions that you know from the energy versus entropy scenario based entirely on entropy, and even more than those. And I have just given you only a few examples of the variety of those that you get in soft matter systems. So this is part of my own work. I'm going to skip it because I would be too long, but I'm just wanted to tell you that you can also get a variety of crystals, BCC, FCC. This is a base, which is an orthogonal system, a diamond crystal based only on entropy, but I am going to skip that. I'm also going to skip some other work that I did on more exotic crystals and just go to my last slide, which says, well, for a long time and also throughout our education, we tend to think that entropy is, the ugly duckling of statistical physics, is this kind of thing that always causes disorder and is going to make the every system look chaotic and so on and so forth, and therefore we have been treating it actually in a kind of a discriminatory way. What my point was today, and I hope I've been able at least to make you think about it, is that our ugly duckling actually can be a very beautiful swan, and that appearances can be deceiving. So with that slide, I would like to come to my conclusions and to my acknowledgements. I have been working on entropic phase transition and entropic system for a good part of my research activities, and therefore I'm very thankful to colleagues and collaborators who helped me myself understand what entropy is and what it can do, my students and postdocs. I thank once again the organizers for this invitation, and I thank all of you for your attention today. Thank you very much. And I am very happy to take any questions, provided I can find out how I can make everybody. Okay, or maybe you unmute yourself. I think you can do that. And if you have any questions, I'll be very happy to take them. And remember that there are no silly questions. All questions are good. So please go ahead. Marianne, can you unmute yourself so that we see if you are unmutable? Yes, Denmark is unmuted. Okay, and I suppose also Mariana and others can do that. Okay. So any questions? Aha, on the chat. Let's click there. It is Ivar to everyone. What happens with entropy around black hole? I was afraid this question was going to come, and I'm going to punt because I have no idea about general relativity. And so any answer I can give you will be nonsense. I don't know the answer to this question. To be able to address this question, you have to have a very, 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 very deep knowledge of general relativity, and there are very few people who can do that. And this must be combined with a very deep knowledge about entropy. So I would say, I estimate there are probably a dozen people who can answer this question. Lenny Susskind, I don't know, a couple of other geniuses, not me. Sorry, Ivar.
Hello, can you hear
Hello,
me?
who's that? Yes?
We're from Denmark.
Yes.
I'm Tommaso. I want to ask a question regarding the I think the last informational slide you had about the force of the big particles stick together.
Yes.
In this interpretation of this entropical force, the force would be zero when the particles are far enough apart, right?
Absolutely, yes.
So this force is actually a little bit different than the usual force, let's say, because it has it only applies when they are actually close together.
That's
right?
absolutely correct. Let me draw something on a piece of paper, which I'm going to hold then on the screen, since in the absence of a physical token, which I can draw, which I could draw on a blackboard. Now I have to draw on a piece of paper, but we're going to do it. Very much. I'll be with you in a moment. So, good. So let me show this. So this is. Can you see my screen? Can you see what I'm holding up?
Yeah.
Yes, you can. Or shall I stop the sharing? Maybe. Let's see. Oh, I don't know if it helps. So let me hold it like this. This is the interaction potential that you obtain between the two big particles, okay, in the presence of the small ones. You have a hard sphere interaction if the distance is smaller than sigma, and you have this attraction that goes from sigma to sigma plus delta, delta being the size of the small sphere. So as you pointed out, Tommaso, now you take the derivative of this, will give you the force. You have an attractive force only for this region, and the force vanishes at larger distances, right? And is that what you said, right?
Yes, exactly.
Right. So it is a force that vanishes identically, but this is true only for this particular model in which the green particles are non-interacting. In reality, there are remnant interactions, again of entropic origin, between the small particles, which is going to modify the interaction in a way that I will show now with a blue line. So the real interaction will look a little bit like that. You're going to have some oscillations, and these oscillations, this wavelength is given by the particle size. And this looks a little bit like the Friedel oscillations you get in liquid metals if you integrate out the electrons, look at ion-ion interactions. So this force is not strictly zero in reality, but it decays slowly.
Interesting, thank you.
Welcome. Further questions, please. Now, can I see the chat here? I can. Yes, yeah, see, I have the overview, yeah. There is I hope I'm saying your name correctly. It's Vietnamese. When you explain U equals 0, I see that you just count the interacting. Okay, excellent question. You see, I omitted the kinetic energy from my considerations for the following reason. Whether you have liquid, solid, isotropic, nematic, whatever you have, the kinetic energy of each particle is 3/2 kBt per particle, right, from the equipartition theorem. So it is the same for all phases involved. It does not affect the comparison or the competition of the free energy between the two. You have, to be complete, I should have written F is, I'm going to write it. So that is the free energy of my phases, 3/2 nkBT minus Ts. But this 3/2 nkBT is the same in all phases, liquid, solid, oriented, disoriented, whatever. So drop it. Does this answer your question? All right, great. Thank you. The thing is, if you like, for instance, simulation, and I think many of you young people are very familiar and very fast, very efficient, you can take, even in 2 dimensions, you can throw rods, or you can throw ellipsoids, or you can throw disks in a plane even, and just let the system run. And you're going to be surprised to see that if your density starts getting high, you will see crystals forming in front of your eyes. You will see the system developing order, but all that you have there is just entropy. So you may wish to play with that. Convince yourselves. It goes extremely fast in today's on your laptops. You'll have in a few seconds, you'll have your result. Let's see, do I see any further questions? I wait a bit more. Don't see things coming up. Marianne, do you want, or someone from Denmark, you want to take over and bring this to a closing, I guess, unless someone else has a last minute question?
So I think we had our questions from Denmark. It was Tommaso who posed the question. I think there are no more questions here. Yes.
Yeah, my fellow Greek, Ioannis Theodonis, is asking whether there's a connection with Shannon's entropy. Yes, there is a connection with Shannon's entropy. It is also defined as logarithm of the states, but it's logarithm with the basis 2. I mean, that's trivial. They just, the computer science like, of course, the binary system. There is a connection with Shannon entropy in information, but I'm not sure, because I'm not a computer scientist, whether there is a second law of thermodynamics in information theory. Ioanni, do you know anything about that? It's the same entropy, but I'm not aware of a second law of thermodynamics there. A spontaneous process and so on. So that is my short question. And certainly Shannon was inspired by Boltzmann in defining that entropy that he did. Quantum, yeah, right. Quantum information. That's right. I have seen that kind of thing, but I'm not sure that you have a similar principle there. I'm not sure about that. I'll have to pass on this. But it's a good question, a good direction to explore. Thank you for this question. Yeah. So yeah, you're welcome, Ioanni. Mariana, you take over.
So I think it takes some time to type in the questions, but perhaps we waited long enough now. So I think it's time to close the morning session. Thank you, Christos, for your beautiful talk. Thank you for the deep insights into thermodynamics. And thank you for promoting the ugly duck entropy.
Yes.
It was a great pleasure, and I think it was very surprising that entropy can create order. Thank you for that. Thank you for your time, and all the best to Vienna.
Thank you for your invitation, and once again, my congratulations for your great Veranstaltung. I'm sorry, my English is going away, and to all of the leaders for their time. We appreciate that.
Okay, thank you very much.
Have a good time.